So thank you, Fabio, and of course, thanks to all the organizers for inviting me. So this is some overview on how to treat shape uncertainty problems in an efficient way. So maybe the background is I am since many years, and before I started to work on uncertainty quantification, I already did shape optimization, and shape optimization has the difficulty that you have to compute or to solve a PDE for many different domains. And of course, if you do shape uncertainty quantification, there are even more different domains. And you really have to think of how to do this in an efficient way. So if you want to go beyond just, let's say, proof of concept and toy problems. I have no idea. Don't want to go to that. So the problem is that I can't even use the mouse, the pointers. So, yeah, it does not. No. Now it's somehow working. So let's see. Okay. No, it's just you have to pray a little bit. Okay. So this is joint work with many authors, so Jürgen Dölz and Michael Multerer, who have been my PhD students, Marc Schmidlin, who is still my PhD student, and Carlos Yeres from Santiago de Chile. I will give a motivation, so why I am interested in random domains, and then I will present the domain mapping approach, which is in principle gives you an exact modeling. There is also the perturbation approach, which I have considered, but I don't. This does not appear in my talk. So since there you make a modeling error. Then, yeah, if you want to go to large-scale problems, you should think about multi-level techniques, so multi-level quadrature. And then you need to prove mixed regularity. And then the methods, so I will motivate this, that maybe finite elements are not the best method to treat such problems. So I'm in favor with boundary element problems, but then you have also some difficulties if your quantity of interest lives on a domain. This is why we started to do the coupling of finite elements and boundary elements. And then in scattering problems, so there your domain is even infinite. And this is done purely by boundary element methods. And we developed also some techniques there which are quite helpful. So finally, I will give a summary. So first, the motivation. So my fruit flight, at least in the beginning, is just the Poisson equation. Let's for sake of simplicity, we have homogeneous right-hand side, homogeneous Dirichlet data. Right-hand side should be given in a large set. So this is not domain dependent. So in principle, you have here for a trace operator, or here you have a, so this lives in the whole space. Okay, in the so-called hold all. So for all realizations, this is well defined. Okay, and in principle, of course, you can solve elliptic PDEs, in particular the Poisson equation, to arbitrary accuracy, but if uncertainty comes into play, this does not really help. So simple applications are tolerances in the shape of products. So you design at the computer, and in practice you have manufacturing tolerances. So what you simulate does not fit to reality. So these are, of course, small perturbations. So larger perturbations you would have if your domains are measured. So in inverse problems, so then it is not clear. So you have, due to measurements errors and ill-postness, you will have a shape uncertainty. And of course, if the shape is somehow given per definition, let's say a cell membrane, so it's not really clear where's the interface. Yeah, it's unsharp. Okay, what I'm interested in is expectation of the solution, correlation, and variance. And of course, so I start always the modeling I have for the domain. I have given the mean in the 2-point correlation, and I'm interested somehow in a quantity of interest or expectation and correlation of the solution. Depends on the problem. So, and if you now start to think about domains, then in principle, you can have a look to mechanics. So they are quite familiar with it, with this situation. So you have a domain, you can deform it. So let's say we get this domain. And then you have somehow to say if your spatial coordinates are also deformed, yeah, then this set becomes a deformed set, or if your spatial set is just the same as before. This is the difference. So are the interior points moved or not? So do you fix the coordinates, or are you in the deformed coordinates? So this is the Lagrangian specification. So, and this enables, of course, since all the interior points are always interior, for large perturbations. And with this Eulerian approach, of course, you can just deform the domain in such a way that this interior set is still interior. So I will go for the Lagrangian specification. So since this allows for large deformations. So in, now, how to model this? So we consider random domain variations. So we have some nominal domain, and then by a vector field, we can deform it. And this vector field should be now random. And this gives our set of random domains. And of course, you can deform it very much. What we need is that the deformation field has some smoothness. And in particular, it always defines an bijective mapping. So, and this is ensured if you look to the Jacobian, and the minimal and the maximum singular values are bounded from above and below. And for analysis, it is we consider C2 smoothness of the deformation field. The domain itself can be unsmooth, so just polygonal domain. Okay, so what we need is, of course, this, as I already mentioned, this right-hand side F should be defined in all the realizations. And this defines then the class of deformed domains. Okay, and then let's go to the variational formulation. So we have the standard variational formulation for the Laplacian or for the Poisson equation on the deformed domain. And the basic idea is now, so this is also in shape optimization, you say material derivative, you just transform it back to the nominal domain. Then you introduce this coefficient matrix, which is the Jacobians transposed times Jacobians to the power -1 times the determinant. So this gives you the coefficient of your differential operator. And then be careful, you also have to transform the right-hand side back, and this gives you a right-hand side. And so here, the coefficient, in particular, if you think of, let's say, piecewise linear Karhunen-Love expansion, the coefficient will be piecewise constant, but left and right-hand side are correlated, so you cannot use here just the techniques for affine coefficients, although this coefficient is affine. The right-hand side depends on the coefficient, so it's a nonlinear problem. Okay, but you are now on the nominal domain, and then on the nominal domain, you can now define expectation and variance. Just for the transported object, domain is fixed, then on the nominal domain, there can also be then defined quantity of interest. Okay, now for the modeling, as I set, we assume that we have an expectation of the field and the covariance. And expectation, I assume for sake of simplicity, it's just the identity. Then the nominal domain is the expected domain, so this makes sense. Otherwise, I can redefine the nominal domain. And then I have the eigenvalues and singular values and so eigenvalues of the covariance operator and the eigenfunctions. And be aware that these phi's, these eigenfunctions, are vector valued. We have a d-dimensional field. So the correlation matrix is, or the correlation kernel is a matrix. So this is already computational demanding to compute the Karhunen-Love expansion. Okay, but this is somehow standard. We assume then, so this is modeling, that these YKs are, the random variables are uniformly distributed. And let's say minus a half. And if you think of log normal, so this would not be allowed, since then the domain has some non-vanishing probability to deform, to degenerate. So you need bounded random variables here. Okay, what we assume is then that we have a certain decay, and what we need, since we have to compute the Jacobian, we need the derivative of the field. So we need that sigma k, phi k in the W1 infinity norm should be summable. So I have considered here a finite sum, but this is a constant which is uniformly bounded. So m can also go to infinity. Yeah, and of course I marked here in red a 2. I want to have even 2 derivatives. So this is to get mixed regularity in order to apply multi-level quadrature. Okay, and then the standard trick, we replace the random variables just by variables yk on the unit cube, and then we get our metric problem, which we need to solve. And expectation invariance would be a high dimensional integral, and for each yi we should compute. So then you use a quadrature method and you have to compute samples. And of course here for each sample we are still on the same domain, but this I will discuss soon. So maybe first some remark on the regularity. There's of course also related work by Fabio and Chris. So this is what we proved is real analyticity, and in the H1 norm, so the energy norm, this was basically the PhD thesis of, that time he was still named Peters, now it's Multerer. And we did also the mixed Sobolev regularity I did with Mark. So you have the standard estimate somehow if you look to the derivatives of your transported functions, and now in H2, not only H1, then you have this standard decay estimate. In this gamma alpha, you have the decay of the singular values times the eigenfunctions. And so this in particular means the higher the dimension, the less important the expression becomes. And in particular, this estimate means you have mixed smoothness, which is, my point of view, which is needed for a sparse grid approximation. And this is my point of view on, or my interpretation of multi-level quadratures. Okay, maybe for implementation, so this was somehow, PhD students are lazy to some extent, which has mathematicians maybe in all, which has advantages. So what we did in the implementation was just to use the piecewise linear approximation of the Karhunen-Love expansion. Then if you compute the coefficient, the Jacobian is piecewise constant. It's a piecewise constant coefficient. And this means, okay, what you can do is you can now compute. So let's go back. This is the transported variational formulation with a piecewise constant here, and here is then a piecewise constant Jacobian. You can compute with a diffusion coefficient on the reference domain, or you can just say, okay, I have my mesh stored with points and elements, P and F. This is as I had learned it. You map just the points, keep the elements, so then which means you change to the deformed domain. So you go from this formulation to this formulation, and then you just solve on the deformed domain. Then you don't have to compute a coefficient. It's still Poisson equation. And of course, if you have a multi-scale or a multi-level hierarchy here, you have it also here. So multi-grid also works. Okay, so this was just for implementation, but we will see that this will cause some problems. Okay, next I will comment on the quadrature. So we have to solve a high-dimensional integral. So then we need a quadrature rule just on the unit cube. And of course, you can use Monte Carlo. I'm not so in favor with Monte Carlo since it's not clear what comes out. I prefer the deterministic quadrature rules. So then you have the quasi-Monte Carlo. Okay, the stupid way would be to use a tensor product quadrature. But of course, if we have analyticity, in principle, it gives exponential convergence if you use Gauss rules. But of course, you can also use sparse grid. And what I want to have is a sequence of quadrature errors, since I want now to play a game with a sequence of finite element meshes or spatial discretization and a sequence of quadrature methods. So this is this slide. So I have somehow a sequence of finite element discretizations. I have a sequence of quadratures, and then the standard sparse grid construction is you split this just in a direct sum of complement spaces, which are define the differences between the spaces. And then the sparse grid space would be you don't use the full tensor product space, you go just to the sum L plus L prime smaller or equal to J, so to the L1 norm of the coefficients. Of course, so what does it help? In fact, if the spaces, the number of degrees of freedom in the spaces form a geometric series, then basically the complexity of the sparse grid is the maximum of this space or this space. So you beat the curse of dimensions. So possibly there is a log if the dimensions are equal. Otherwise, you even do not have the log. And the approximation property is the same, basically, except for log, if we have the mixed regularity, which we have proven. Okay. But in practice, usually you don't want to have these W spaces, so you can generate them by wavelets. But of course, you can then just say, okay, the Vj is just the sum of the Wj. You can sum up the rows. Then you see, okay, this is just a single space, or you just sum up the columns. You have a W space times a single scale space, W times V, and so on. You build slices in this direction. Of course, you can do it also in the other direction. And this gives you now two formulas. Namely, okay, you can say the W spaces are nothing but the difference of the V spaces. So then you have the sum. You go through in this direction, you sum up, and you have the difference between the product of VL times Vj minus L minus the product, tensor product VL minus 1 times Vj minus L. Okay, this is the standard setting in the multi-level Monte Carlo, let's say. Yeah, with a difference of finite element approximation times the Monte Carlo method with different accuracies, but this is nothing but the sparse grid combination technique. And of course, you can do the summation also in the other direction, which gives you also some nice approach, which is completely equivalent. You have just the finite element solutions times the difference of quadrature formulas. And of course, if you use nested quadrature formulas, this saves some complexity. And both are really exactly the same. It's just you change the summation. Okay, but where are the drawbacks? So I just said, okay, we can map elements. So the approximation is canonical, piecewise linear KL for the field. Then you get piecewise constant coefficients. But indeed, if you are on the coarse grid, and you have a triangle which is mapped to this point, and this point. It's a triangle like this. If you then go, and what you see is the mesh, the triangle, what you get is this one. If it's with straight lines by this discretization, and this has a negative determinant. Orientation is flipped. So this causes problems. And in particular, you have to be careful. Of course, the argument from a theoretical point of view, just say, okay, my resolution needs to be fine enough. But in practice, this is somehow a problem. And of course, now this is experience from shape optimization. If you use just boundary elements, you are just on the boundary. And there, mapping meshes is much more robust, much easier. So this is why I'm in favor then, when we saw this problem, in favor with a boundary element approach. Okay, maybe one comment here to avoid this problem is, of course, what you can do and which should work, if one thinks about it. So we have a proof that, let's say for log normal coefficients, you can do just a piecewise approximation of the coefficient. And then what should work is if you on the finest grid, if let's say in the midpoint, you evaluate your KL and then use this point just as approximation to this piecewise constant coefficient. So this should work, but if you say, okay, I use my KL for the different levels, I use the restrictions, then this causes problems since maybe determinant becomes negative. Okay. Okay, where this problem does not show up, coupling of FEM and BEM. So what is the idea? So we have this, so the basic idea in boundary elements is, okay, don't go to the fixed domain, since there you have varying coefficients. Go to the deformed domain, since there you have constant coefficients, and then you can apply boundary element methods. So basically we have the Poisson equation, and now, of course, why not using pure boundary element methods? Okay, let's assume we have on a subset B, our quantity of interest lives. So maybe I will consider my numerical example an L2 tracking type on this set B. And then, so this goes back to a reviewer who said, okay, quantity of interest makes only sense on a part of the domain which is not deformed. So we assume, okay, that the deformation field on the set B is just the identity. Deformed is everything else. Okay, and then you can apply here finite elements, fixed domain. And the rest is coupled and treated by boundary elements. So usually in coupling, you say with boundary elements, you go to infinity. So this outer boundary is somehow artificial, but I did it once for shape optimization. And okay, so then the basic idea is you write down an interface problem and since we have the F here, and with boundary elements, you can also only solve a homogeneous equation, basically. So in an efficient way, we can introduce a Newton potential, which resolves the inhomogeneity. And this can maybe be computed in a big box with your multi-grid method, whatever you like, without any, so with boundary conditions you like. Yeah, it's just we can then subtract from the unknown function u this Newton potential, and then we are looking for a homogeneous function. Okay, and then the basic idea is, I do not like to go into detail. You do a boundary integral equation, so you have the single layer operator, which is the v. You have a double layer operator, which is the k. There's a k, here's a k. K transposed is just the adjoint double layer. It's transposed system matrix, and then you have the W, which is the hypersingular operator. So in principle, you consider two integral equations on this interior boundary. So this is for stability reasons. Then you end up with a elliptic problem, and then you have one boundary integral equation at the forming boundary. And then the discretization is, of course, you have finite elements on the ZB. On sigma, for the Dirichlet data, you use the traces of these finite elements, so piecewise linears, Neumann data approximated by piecewise constants on the induced mesh. And at the exterior boundary, you use also piecewise linears and piecewise constants. Okay, and maybe this sounds complicated, but you can show if you do BBX preconditioning on B, and I use for the boundary elements, so which gives you dense matrices, I use wavelet matrix compression, and then you can precondition, and you can overall build the optimal preconditioner and can solve this in linear complexity, the whole problem. Okay, does this work in practice? Indeed, it works. Well, this is, you see the finite element mesh. Here we have just the boundary elements, quantity of interest lived on B, tracking type functional, so U square basically. And then, okay, this now depends on what you want to have. If you choose your quadrature rule. So what we did here is a quasi-Monte Carlo method. And if you just double the number of points from level to level, so then you get linear convergence. But of course, you can think a little bit that U square, you should be able to approximate this with quadratic order with finite elements. So problem is smooth. If you increase, if you just choose the number of points by a factor 4 from level to level, you get also the higher rate of convergence. So these are the levels. This is the accuracy. And then we did different number. So this just on the finest level, we chose a fixed number of samples. So 10, 25, 50, and then we increased the number of samples. So this can be done in a efficient way. Okay. I will then go a step further. So this was 2D. Let's go to 3D. It's even more complicated, and we considered scattering problems. So what is there the problem? So we have some scatterer. We have some incident field, and okay, at the scatterer, this field is scattered, and one is interested in the outgoing field or in the total field, which can be computed if you know one of these fields. And what you know, the equation behind is the Helmholtz equation. So at infinity, you have a Sommerfeld radiation condition. And of course, the domain is now unbounded. So it's not really possible to, so not in a naive way to use finite elements to solve this Helmholtz equation. And this is a standard application where you use in principle boundary elements, since then you have just a boundary integral equation at the surface of the scatterer. Okay, what we want to compute is somehow the expected scattered field and its variance. Maybe you are also interested in the far field, so this would be at infinity. There you have also a direct formula, then you compute an integral over the sphere. Okay, so the boundary integral equation, so which is, to my experience, the best one here, is to use a combination. So this is Brackhage-Werner formulation, a special one, which should find in the book of the experts, Gress and Colton, and with a nasty right-hand side where you do a linear combination of the incident field, but this gives you indeed the Neumann data of the total field. So the Dirichlet data are known, so you know then Dirichlet and Neumann data of the total field at the scatterer. Okay, and then to compute, so we have then Dirichlet and Neumann data here, and to compute the solution in any point in space, you have the representation formula. But of course, what you see is to compute this axis now, let's say Eulerian coordinate, it's fixed. So you fix the point, you can compute the scattered wave. But this is again a boundary integral. And if you have to compute a lot of points, this again becomes extremely expensive to do this evaluation. And in particular, so this X is somehow fixed. So let's put an interface around all the random scatterers, and then outside the interface, everything is fixed. Maybe inside it's moving. It's not clear. So one advantage of just moving the boundary is also that you do not know what happens in the interior. This helps you also in inverse problems when you maybe know only the boundary of the shape, but you have no insight what's going on inside. You are not interested in how to move the inside. Okay. And if you think we have a fixed interface, so then maybe one can have the idea, if I know the expectation at this fixed interface, the expectation of Dirichlet and Neumann data, I can use again this trick to compute the expectation in any point outside by the representation formula. And to get the variance, you can go to this trick. If you know the covariance, then you can also compute the variance everywhere outside. So this is now what's going on here. So we compute, so the basic idea is we compute expectation of the Dirichlet data and the Neumann data at this artificial interface sigma by a sampling method. And you are far away from the scatterer, so solution is smooth. You can do here really a higher order approach. Yeah, few points, high order interpolation or something else. So this was the idea. And indeed, if you go for the correlation, then you can later on also compute the variance of the solution. But if you go for the correlation, you need then in all the points you want to evaluate the covariance on the interface. You need the covariance matrices, the correlation of the Neumann data with itself, the correlation of Neumann and Dirichlet data, and so on. So which can be large if you have 1,000 points. These are again 1,000 times 100, 1,000 points. And the basic idea is, as I told you, you observe that the solution is smooth, you are away from the interface. So these matrices can be compressed. So if you plug all together, you have a symmetric positive definite matrix, and you can just use a pivoted. So you have to calculate them completely, but afterwards you do just a compression in order to have a fast evaluation in the exterior field. Okay. The implementation is done with boundary elements, so we use the isogeometric boundary element methods. Since there you also have by construction, you use splines, you have a multi-scale hierarchy, so you can do again multi-level approximation, and indeed in this Bembel, so we built in a multipole acceleration, so it's a fast method and solves your boundary integral equation in log linear complexity for any desired polynomial order P. And now we still have somehow to compute the deformations, and this is some speciality of this isogeometric approach. So since there, the basic idea is you have your geometry, you parameterize the geometry by four-sided patches, and then you have mappings. And these mappings are NURBS mappings or spline mappings. So, but they can also be parametric. So this can be done for arbitrary complicated surfaces. But then on your four-sided patch, you start to refine, and this gives you the mesh on the surface. And then you can define your splines by mapping splines from the unit square to the surface and maybe gluing along the interfaces to get C0 splines. These gamma I are smooth. And this means if you know the surface values in the grid points, you can do a local interpolation. So this is what we do. Of course, to deform a spline surface, you can start to deform control points. But the most efficient thing was you compute the deformation field in the grid points on the reference surface, and you just map grid points, and then you do a high order local interpolation such that consistency error is okay. Yeah. Okay, so this is basically what's written here. So you do the KL only in the grid points, you map just the grid points. This gives you a surface, and then you start your boundary element code. Okay. So some example. So what we have here is a brick with 6 holes. So this is our scatterer. Outside, so our fixed surface we choose is a cuboid outside this brick with holes. So on the cuboid, we compute expectation and covariance. So the covariance field, also the perturbation field, we consider expectation is identity. So from this brick with holes, and this is our covariance kernel. So we see here the decay, and we work in the numerical expand examples with more than 130 dimensions. So wave number, of course, if you're somehow familiar with scattering, so we choose kappa equal to 1, since there is again high frequency. If you have a high frequency, the multi-level idea would again not work. You have to resolve the wavelength. So low frequency case. And okay, we consider B-splines, so of degree, so piecewise constants, piecewise linears, piecewise quadratics. I have to say already piecewise constants have a high accuracy in boundary elements, so higher than piecewise linear elements, piecewise linear finite elements. So P equal 2 is already very high order, so gives you convergence rate, I think h to the power 7. The problem is P equal 3, it wouldn't have been a problem, but we will see the big problem. We combine this with a sparse grid approach or with a Monte Carlo quadrature, so based on Holton points, which gives you linear convergence. The problem is we have an extremely high spatial convergence rate, but the stochastic method, the convergence rate is not that high. And for P equal 2, from level to level, you have to increase the number of quadrature points by a huge amount, and this kills you, even if you go to parallel computers. Now, of course, one can think about applying higher order quadrature methods to reduce this mismatch. Okay, then since Lorenzo asked this question the last time, the sparse grid approach, sparse grid quadrature we use is an anisotropic one. So adapted to the decay of the singular values. Okay, these are the examples. You see here the brick, so 2 deformations. We have considerably large deformations. So these are then the solutions on this artificial interface of the scattered wave. So they look, they look indeed different. And then we have here the number of boundary elements. So, okay, for piecewise constants, you can go up to 20,000, which is not very much, but the problem is the number of quadrature points. So this was the bottleneck here, the surprising bottleneck somehow, since I was not aware of this. So for the quadratic splines, we go just to 3,000 unknowns. Since if you now look to the quadrature points for these 3,000 unknowns. Okay, you use here for the quasi-Monte Carlo, we have 16 points on the finest grid, but then you already have 1,000 for these 1,000 unknowns and 65,000 samples for the 738 unknowns. And with a sparse grid, which behaves worse, we already have here 800,000 unknowns. So adding another level would be not possible to do anymore. So the number of random samples was just on the causes grid was somehow the limitation here. And for cubic splines, of course, you even have to increase the number of unknowns even more, the number of quadrature points. So this is not feasible anymore. Okay, the whole thing has been done on a parallel computer and so on. You can start a computer. So Jürgen did this in Bonn. And then indeed, you observe the predicted convergence rates. So this is what you here see for QMC and for the sparse grid quadrature 2. And okay, also a comparison to a direct evaluation. So in all, the method works. But here the limit is somehow the quadrature method we use. So we should use a higher order quadrature method. Okay, I come to the end. So what I considered is the solution of boundary value problems on random domains, so elliptic ones. So what I have is I have regularity estimates, at least for the standard second order diffusion problem, not really for this scattering problem, since there you have to exclude that you get a resonance. But this mixed estimate, so this is the theoretical foundation that multi-level quadrature work, so we can prove it. And then, of course, in realization, you face problems, and there's the idea then, okay, use boundary elements and work on the deformed domain, which is maybe not the canonical approach. I think most people say, okay, I use my fixed domain and I compute the coefficients, but basically, if you just map the mesh, you can do it in MATLAB. You have your mesh points, your vertices, you map them and use the standard MATLAB PDE toolbox. So it's very easy to implement. But okay, this is, if you are on the level that you say you can work on the deformed domain, then you can also use boundary elements there. It's completely the same. Okay, so this is the last point, that boundary elements have really advantages if you deal with random domains. And usually, of course, you can say with boundary elements, coefficients need to be constant. But in many applications, this is the case. Maybe you have jumping coefficients, but then you can again use boundary elements just on the interfaces. So this is known. So I'm not aware of so many equations where you really have non-constant coefficients, non-constant coefficients. So at least from my experience with shape optimization. Okay, references. So this is the paper with this real analyticity in the energy norm. This is the one with the mixed regularity and also with this coupling approach. And this is the work on the scattering. So thank you very much.